I need to ask that question. Oh, I never tried that. Okay, folks. Before we get started, I do have a question for you. So today we are supposed to have a lecture during lab. So my question that I'm going to pose to you is this. We can either meet in person in 206 or we can all just join Zoom. Now, there's advantages and disadvantages to both. The advantage to meeting in the classroom is, for the most part, you can guarantee your attention will be held because it's a little less likely that you'll want to do other things when you're sitting there in front of the professor. That's just human nature. So that would be the advantage to being in person. Now, the advantage to being in Zoom is you can stay in your room and you won't have to come sit on those uncomfortable chairs. So this is a vote. I always go with majority rules, as you know. I'm not changing that. So this is going to be a vote. You will decide how we do it. Yes. It will likely, it all depends upon how much I get through to this morning. But I am going to guess we will be there for a couple of hours. Now I will because we will be there for a couple of hours, I will give you a break in between. So about a 10-minute break. But I'm going to guess it's going to be a couple of hours. Other questions before I take a vote? And goodness, there's a lot of people on Zoom this morning. So all those that would like it to be on Zoom, raise your hand. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So on Zoom, I'm looking at 14. And of course, there's no markers up here, but that's okay. I can remember 14. All those that want it in person, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9. Zoom looks like it's going to win today. So we will use the same Zoom channel that I use for class. In other words, if you look at today's lecture, there's a place to click here. It'll be the same Zoom link. And yes, I will still be able to take roll as to who comes because I can go back in and look at the roster for Zoom. So I'll know who's there. Now I will ask that since we're going to be on Zoom, I will try to make it more so that can help keep you awake. I'll try to make it a little bit more interactive. So that's how I'll do that. Questions? Okay, other than this first part, which I'm just trying to get your brains in gear with this morning, what I'm going over today, both in lecture and in lab, will not be on your exam. So again, this first part, yes, because I'm basically just trying to get our brains going at 8 o'clock in the morning. And it is over the topics we discussed on Tuesday. But again, once I get through with this, what's up there now, and I move on to covalent molecules, starting with covalent molecules, it will not be on your exam on Tuesday. Okay, so what I would like to do is I would like to give you some time. You can chat among neighbors, stuff like that. But I want you to go in and I would like you to try to answer these. Because that's how you're gonna see it on the test. You're gonna see them all mixed up and you gotta figure out what's what. And then I'll talk through how I look at things. Huh? No, PT is that. Go, just send it forward. If you've already signed, just send it forward, because I don't know, it doesn't always make it. Okay, folks. I'm going to focus on the formulas first, and then I'll come back to the names. And yes, even when I should say, when I was learning to do this, I would do the same thing. Focus on the formulas first, get all those, then I'd come back to the names. Now, with the formulas,
the first question I ask myself is, does the metal always have the same charge? That's the first question I ask myself. Does the metal always have the same charge? So, does cadmium always have the same charge? Yes, it is in that little stair step on the right-hand side that always had the same charge. Does platinum, which is element 78, always have the same charge? No. Now, the reason I did that is because when I say no to something, that means I'm going to need a Roman numeral. So this is a way I'm reminding myself, I got to have the Roman numeral in that one. So, but if I said yes, does that metal have the same charge? Then it's just a matter of naming the metal and naming the anion. So in this particular case, the metal is cadmium. The anion is one of our polyatomic ions, and it is the polyatomic ion nitrate. So the first one should have been just cadmium nitrate. Now, for the second one, I said, hey, I am going to need a Roman numeral. Because I need a Roman numeral, that means I'm going to have to figure out what Roman numeral I need. I have one platinum, and I'm going to give it a random variable for its charge. I have 2 peridiotates, and periodate, knowing that I have iodine and it is in group 17, that means that this is a -1 charge. So I have 1 times Y minus 2 times 1, and that is going to be set equal to 0 because ionic compounds are always charge neutral. Y minus 2 is equal to 0. Therefore, Y is equal to 2. So that just allowed me to figure out what the charge on the platinum was. So to name this, it's going to be platinum. I will use the Roman numeral for 2. And then I need to name the anion. Again, this is a polyatomic ion. It is the periodate ion. And folks, the reason I knew it was periodate is because I knew what perchlorate was. And iodine is right under chlorine. So it's the same thing. I'm just substituting in the iodine piece. Yes.
But you don't see that there's the 2 outside of the parentheses.
In this particular case, that would have worked. But remember, when we make ionic compounds, we cross, drop, and simplify. You have to make sure you didn't just simplify it. So it's always better to do the formula because then you don't take a chance of screwing up and not realizing that the formula had been simplified. Other questions? Yes. Cadmium's always a +2. So remember, and this is super, folks, this is super important because as you saw, the very first step I did was, does it always have the same charge? Group 1 always has the same charge of a +1. Group 2 always has the same charge of a +2. Silver always has a charge of a +1. Zinc and cadmium always have the charge of a +2. Aluminum, gallium, and indium always have the charge of a +3. If it always has the same charge, you don't have to specify the charge. So you got to remember those guys. Because they're always the same. So they don't need a Roman numeral. All the rest of the metals,
you have to have that Roman numeral.
Okay, moving on. The very next thing I'm doing is, okay, now I'm into the names. And I look for specific things when I'm doing names. I look for Roman numerals because that's going to tell me the charge. I look at the ending of the anions because that's going to tell me, for the most part, what type of ion I'm dealing with, polyatomic or elemental. So with naming, it's a matter of translating and then cross drop and simplify. So lead 4, so that means, whoopsies. That means my lead is a +4 charge. And then oxalate, the ending ATE tells me it's a polyatomic ion. Oxalate is C2O4 2-. You're going to take the magnitude of the metal and cross and drop it onto the anion, and you're going to take the magnitude of the anion and cross and drop it onto the metal. Yeah. So on our lead, we will initially place a 2. On our oxalate, we will place a 4. Because you needed more than one polyatomic ion, the polyatomic ion itself goes in parentheses with the quantity needed as a subscript outside the parentheses. But here's where you got to remember the last piece. You got to simplify. Both of the subscripts you just dropped were divisible by 2. So you have to do so. So the formula for this actually is PP C2O4 2. Which comes back to your original question, Brislin, about can you just backtrack? And this is why you can't just backtrack. It's always better when you're dealing with formula to start with the equation. Now the other one, again, you're going to translate. So we have barium. Barium is in group 2, so it's always a +2. And you have bromide, the ending IDE, except for hydroxide, cyanide, and peroxide. Other than those 3, the ending IDE says it's an element. So it's the element bromine. And since it is an anion of bromine, bromine's in group 17, so that's a -1 charge. We do our cross, drop, and simplify, and you get BaBr2. Hopefully after the homework, it's getting there. But I also wanted to wake us up a little bit. Okay, any questions over ionic compounds? So what are you going to expect on the test? There will be a section where I give you the formula or the name of ions, and you give me the opposite. So if I give you the formula of an ion, I'm asking you for the name of the ion. If I give you the name of the ion, I'm asking you for the formula of the ion. There will also be a section, which will be a little bit like this, where I'll give you the formula of an ionic compound and ask for the name, or I'll give you the name of the ionic compound and ask you for the formula. What I was doing with you on Thursday and Tuesday was trying to give you information that would reduce the memorization, how I figured out the formulas. But you're not going to have to figure out the formulas if you know them. It's just, I I was giving you information as to how you can, I was giving you the information as to the trends. So there was less memory work. That's all. And the reason I brought that up is because I was sent an email with that question. So I thought I would share with everybody. Questions about ionic compounds? Okay, if there's no questions about ionic compounds, dang it, I'm having a day. Then we are now going to move on to covalent molecules. Okay, so first of all, how am I going to recognize that I'm dealing with a covalent molecule? I am going to look to see if the formula or name consists of nonmetals and metalloids only. If it consists of nonmetals and metalloids only, then that's going to be a covalent molecule. Now, covalent molecules contain covalent bonds which arise through the sharing of electrons between two atomic nuclei. Now, what I really mean by that, let's take something as simple as hydrogen. And we're gonna make a covalent molecule of two hydrogen atoms. So if you'll recall, the hydrogen atom has a proton in the nucleus, and then surrounding it in the first shell, it has an electron. So for both of our hydrogens, you've got the proton, and in the electron cloud, you have an electron. Now, what happens is when these two atoms come close enough together, we get an electrostatic attraction between the proton of one nucleus and the electron of the adjacent nucleus. We get the electrostatic attraction of one proton from a nucleus, of the proton from the nucleus to an electron on the adjacent atom. It's still, folks, covalent bonds is still a type of electrostatic attraction. The difference is in an ionic bond, you have an atom that has a plus charge and you have an atom that has a negative charge. Whereas in a covalent bond, it's the positive is associated with the protons and the negative is associated with the electrons on the adjacent atom. Now, we're not going to get to, we'll get into these bond types in much greater detail starting after fall break. But right now, what we're going to do is we're going to talk about how to name and develop the formulas of covalent compounds. Now, we are actually going to look at 4 categories of naming of covalent molecules. The first category that we're going to talk about are our diatomic elements. The second category that we will talk about is going to be hydrogen bonded with a group 15 through 17 element. The third type we're going to talk about is a specific type called alkanes, which, folks, if you can get the gist of alkanes, it's going to help you when you get to organic chemistry as well. But I go over the alkanes because the alkanes are things that you're going to come across frequently. And then finally, we're going to get into binary covalent molecules. As far as the rules are concerned, to me, covalent molecules are typically a little bit easier from a rule perspective for naming. However, it is more difficult because there's a larger variety of them. So let's get into our diatomic elements. First of all, the prefix di stands for 2. So diatomic elements will be compounds consisting of 2 of the same element. Now, folks, there are other elements that form compounds. For instance, carbon by itself forms diamonds, which has a ton of carbons, or graphite, which has a ton of carbons. You have sulfur, which a lot of times will have 8 sulfur atoms. You have phosphorus, which will have 4 phosphorus atoms. So covalent compounds can form multiple substances that consist of many of the same atom. But I want you to know the diatomics. And those diatomics there are 7 of them. And the easiest way to remember it is Brinkelhoff, at least for me. But I'll show you another way to memorize them in a moment. These elements when found in nature, by themselves, come in pairs. So the formula would be Br2, I2, N2, Cl2, H2, O2, F2. Now, I emphasize found in nature because what does that mean? It means if I say I have bromine, it means I have Br2. If I say I have oxygen in the atmosphere, then I have O2 in the atmosphere. If I say I have nitrogen in the atmosphere, it means I have N2 in the atmosphere. If I say something gives off chlorine gas, it means that it's giving off Cl2. In other words, these 7 elements when found in nature by themselves are always in pairs. Now, I gave you the second way to memorize them. I said the term 7. There are 7 diatomic elements. And if you look at the periodic table, start with nitrogen, they form a nice 7. And then you gotta add hydrogen to that list. So that's the second way you can memorize them. If you really want to look at it, other than bromine and iodine, they're also all gases. They're the gases on the periodic table. But you gotta add bromine and iodine to that. That is all there is to the diatomic elements, is simply knowing who they are and realizing that if they're found in nature alone, they come in pairs. And the name for their formula is the exact same thing as the name for the element. The next category was hydrogen with group 15 through 17. Now I'm going to start this by saying that when I do this particular naming, it's going to be a little bit of a shock to the system for some, but wait until I get through acids and then it'll all become clear. So, first of all, I said that we're talking about the nonmetals and metalloids only. So with group 15, that would be nitrogen, phosphorus, and arsenic that we're going to focus on. With group 16, that's going to be oxygen, sulfur, selenium, and tellurium. Hate when my thing does something weird. And with group 17, that is going to be fluorine, chlorine, bromine, and iodine. Now, if I asked you what charge group 15 nonmetals have as an anion, what would you say? A -3. Well, when hydrogen combines with group 15 nonmetals and metalloids, they do so in a 3:1 ratio. So in other words, the number of hydrogens is equivalent to the charge of that element as an anion. If I asked you what group 16 nonmetals would have as a charge if it were an anion, what would you say? -2. Well, all of these, when they combine with hydrogen, will do so in a 2-to-1 ratio. So again, the number of hydrogens is equivalent to the charge if the nonmetal were an anion. Well, as you can tell from the storyline, that means since group 17 nonmetals are -1, they would have 1. Now to name these folks. We added hydrogen to phosphorus. So we say we added hydrogen to phosphorus. Oops. We added hydrogen to phosphorus. We added hydrogen to nitrogen. We added hydrogen to arsenic. In other words, folks, you don't have to specify how many hydrogens and phosphoruses there were. You don't have to specify how many hydrogens to nitrogens there were, because there is only one way that hydrogen can combine with nitrogen. It's got to be in a 3-to-1 ratio. It's kind of like when we were talking about those metals that only had one charge, because there's only one charge. You didn't have to specify the charge. Because there is only one way for hydrogen to combine with these things, you don't have to specify the number. Now, this storyline is going to work with everybody. So this would be hydrogen sulfide. This would be hydrogen selenide. There is one that this story does not work with in my book. That is because everybody in this entire world knows it by a specific name. I mean, yes, we have, depending upon where you go, it may be called aqua or some other variation, but it is still what? Water. And that is the only name I'll accept for H2O. I mean, yes, you can call it hydrogen oxide or dihydrogen monoxide. But folks, everybody in the world knows it as water, so just call it water. There's no reason to make our lives more difficult. This is one of the few times you're not going to use IUPAC naming. H2O is water. It is water. It is water every day of the week. And yes, I could continue with this hydrogen story over to the group 17, and you would get the same process. And so on and so forth. That's all there is to this section of hydrogen with group 15 to 17. And yes, I did not fill them all in because it's the same story over and over and over and over again. Any questions about that storyline? Okay, let's move on to the alkanes. And as I said, folks, well, let me actually go back a moment. And then I'll come back to what I said. The majority of the compounds that we are talking about are considered to be inorganic compounds. Whether they're ionic compounds, whether they were the diatomic elements, whether they were the hydrogen with group 15 through 17, whether they're the binary covalence. Though what we are discussing is how to make inorganic compounds. But in your second year of chemistry classes, you go on to organic chemistry. And organic chemistry deals with carbon. The very simplest of organic compounds are called alkanes. So this is the only section where I'm going to start touching on organic chemistry. And the reason I touch on this particular section is because you deal with it on a daily basis. Well, maybe not daily, but pretty close. If you fill up your car, you're putting in octane, which is an alkane. If you heat a home, most likely you're using propane, which is an alkane. Upstairs, we use the Bunsen burner. We're using methane, which is an alkane. When you have a lighter, you add butane, which is an alkane. So I go ahead and discuss the alkanes in college chemistry. Not all the faculty do, but I like to go ahead and do so because these are things you encounter a lot more frequently than you think. And so I think it's important that you at least know the terminology. That, and when we start getting into combustion reactions, we're going to talk about the alkanes. So I think it's important that you know these characters simply because they are things that you encounter. But when you get to organic chemistry, you're going to take what I'm teaching you today and you're going to build on it. And it gets, to be quite honest, it can get pretty darn complex real fast. Because when you get to organic chemistry, they have these functional groups. They have alkenes. Alkenes means there's a double bond. They have alkynes. Alkynes means there's a triple bond. They have alcohol, which means there's an OH group. They have amino acids, which means there's an amine group, and there's a carboxylic acid group. They have a lot more naming, in other words, but the naming is all based off of this original naming. So if you'll get down this original naming, it will greatly help when you start to get into the organic chemistry as well. So your alkanes, they are compounds. Why? Oh, why? Just me today. Alkanes are compounds of carbon and hydrogen only. They have the general formula give. Oh, I see what's going on. Somehow I changed my pen. They have the general formula of CN H2N plus 2, where N is equal to the number of carbons. The simplest of all would have one carbon. So it would be carbon 1, H 2 times 1 plus 2, or in other words, it's going to have the formula of CH4. Two carbons would have 2 carbons and 2 times 2 plus 2 hydrogens, or in other words, C2H6. 3 carbons would be C3H2 times 3 plus 2, or in other words, C3H8. 4 carbons, C4H2 times 4 plus 2, or in other words, C4H10. I think you're getting the drift on the rest of it. So they would be C5H12, C6H14, C7H16, C8H18, C9H20, and the last one we'll do is C10H22. So we'll do the first 10 alkanes. I love that question. So I was just asked, do I not simplify? Because remember, with ionic compounds, I always simplified. I cross-dropped and simplified. Ionic compounds, yes. Ionic compounds must be in the smallest whole number ratio possible. Covalent molecules, no. Now, let's talk about how to name these. First of all, the ending, if you didn't guess from my methane, propane, butane, octane, you didn't guess from that. The ending for all of these is ane. So what is the prefix? The prefix tells the number of carbons. The first 4, you just kind of got to get to know. I don't have a wonderful way to tell you how to memorize them. Meth, S, prop, and bute. I mean, I guess you could go MEPB and memorize it by MEPB, but meth, S, prop, bute. So CH4 is methane. That is the gas we use upstairs out of the Bunsen burners. That's also the gas that cows give off. It is a greenhouse gas. Ethane. The biggest thing I can say about ethane right off the bat is ethane makes goes to make ethanol, which is the drinking alcohol. Propane is the gas that's used to heat. Butane is the gas that's typically used in a lighter. Now, once you get past that point, the prefix is the same as the prefix for an object with the same number of sides as the number of carbons. So what is a five-sided object called, such as what's in Washington, D.C.? A pentagon. Well, this is pentane. In organic chemistry, one of the favorites is going to be 6 carbons. And the prefix for 6 is hex. So it's hexane. The prefix for 7 is hept. It's heptane. And the prefix for 8, what is the shape of a stop sign? It's an octagon. Well, this is octane. Now, most people don't get into 9-sided shapes and 10-sided shapes, but this would be nonane and decane. Folks, that's all there is to the alkanes. You know the general formula, and you know your prefixes. And you can work it out back and forth. Questions? Okay. Now for the last category of our covalent molecules, we're going to talk about binary covalent molecules. Di. Whoopsies. They both mean 2. So these are going to be molecules containing 2 different elements. Now, one important thing to note when we get into these binary covalent molecules, and every molecule, I've said this before, and that is, you got to remember, no 2 compounds can have the same formula or the same name. What I mean by this is the name. Basically, what I mean by this is the name and formula are unique. Every compound has a unique name and a unique formula. Now, this is particularly important when we get into the binary covalent molecules, because we're going to have to start to distinguish right off the bat, two molecules that contain carbon and oxygen are CO and CO2. Because these are unique formulas, folks, they also have to have unique names. And this is important because one of these two molecules replaces the oxygen in your bloodstream, and that's how it kills you. Because it's roughly the same size as the oxygen in your bloodstream. One of these molecules, it can still kill you, but it doesn't do so in the same manner. One of them does so by suffocating you because there's just no oxygen to breathe in. But it itself doesn't replace the oxygen molecules in your bloodstream. Also, one of them is a very well-known greenhouse gas. So again, unique formulas, unique properties. We gotta give them unique names. And that's where we get into the binary covalent molecules. So let's talk about naming first. This will be I'm trying to think if there's any other examples. This will be the primary time we use prefixes to describe the number of each atom in the molecule. I wanted to put in that term primary because obviously we've already used prefixes when we dealt with the hydrates. We've used prefixes when we had dihydrogen sulfate. So I didn't want to say we never use prefixes anywhere else because that would be a lie. But this is the primary time you're going to use prefixes. So those prefixes. For one, it is mono. Now, with respect to mono, mono is only used on the second atom. In a formula. If there is only one. For di or two, it's di. 3, tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is Nuna, and 10 is Deca. If you look at the last, well, starting with number 5, you look at 5 on, it's the same as we did with the alkanes. Now with these particular prefixes, they're used on both atoms. To describe the quantities. Now, the last thing I want to make note on about these guys is the A in the prefix will be dropped if the element's name begins with an A or an O. So let's go back to my original examples, CO and CO2. The first element is carbon. The second element we are going to give the "ide" to, so it's oxide. That is true for both of these compounds. But again, unique formulas must have unique names. So with the first one, there is one carbon. Well, we don't use the prefix on the first element. And there is one oxygen, which we do use the prefix for. So that is carbon monoxide. CO2, we don't use the prefix on the first one because there's only one, but we do use the prefix on the second one, so it's carbon dioxide. Folks, the neat thing, well, I shouldn't say the neat thing. Chemists are not very imaginative. Well, I mean, we are, but we're also very direct. You can literally take these names and read them. One carbon, one oxygen. One carbon, two oxygen. And then come up with the formulas. That's what I meant by we're not very inventive. Chemists are extremely inventive, but we're also very direct people. We're going to tell you how it is. We're not going to come up with a lot of fluff. We're going to keep it simple most of the time. Keep it as straightforward as possible. There's enough of chemistry that's tough. I don't need to add any. Okay, so let's talk about other options. Now, I want to show you this one because I see students screw it up all the time. One of these is a covalent molecule. One of them is a polyatomic ion. The one on the right is sulfite. but the one on the left is not sulfite because there's no charge showing. Ite means a charge. There's no charge. So we're literally going to read this. So 1 sulfur, 3 oxygen. 1 sulfur, so that would be mono, but we never use mono on the first element, so it's sulfur. 3 is tri. Oxygen is oxide, so that's sulfur trioxide. But sulfur likes to play around and have varieties of options available to it. So another option would be S2O3. Again, not the ion. In this case, we have 2 sulfur, 3 oxygen. 2 is di. Then we have our sulfur. 3 is tri. Then we have our oxygen. So that's disulfur trioxide. So I guess with these last couple of examples, the main thing I wanted you to note is charge means polyatomic ion. No charge means that it's a covalent molecule. So if I gave you tetraphosphorus dicoxide, to get to the formula, you literally read it. 4 phosphorus, 10 oxygen. So it's P4O10. Questions? That, folks, are the covalent molecules. What that means though is I will be probably using 2 hours. Again, for those that came in late, we're actually meeting on Zoom for lab instead of having you sit on those hard stools and no comfortable backs. We're going to meet on Zoom for lab. In lab, we're going to be going over acids. We're going over formula mass, molar mass. We will talk about how we determine these formulas using, well, it could be using a variety of methods, but elemental analysis essentially. And then we're going to also get into Avogadro's number and do some calculations with it. Yes. When you go on Blackboard, it's gonna have to be on a computer. I found out from somebody that it does not work on the app, but when you go on the computer, when it talks about the class, it says, and the Zoom link, click here or something like that. You just click there and it'll take you to Zoom. Huh? Nothing after the very first piece where I gave you examples of ionic compounds again is on the test Tuesday. Questions? Okay, I will see you on Zoom.